1. What the video is basically saying. Story in one paragraph. In 2016, we found Proxima Centauri b, Proxima b, a roughly Earth-mass planet in the habitable zone of the closest star to the Sun. Media ran with Earth 2.0 backup planet headlines. But Proxima is a very active red dwarf flare star. Proxima b orbits extremely close, is almost certainly tidally locked, and gets blasted by X-rays and UV. Over billions of years, that likely strips its atmosphere and water. And even any twilight habitable strip along the terminator would be an insanely harsh environment. On top of that, interstellar distances make actually going there a monumental challenge. Even our fastest probes would take tens of thousands of years. So, Proxima b is scientifically fascinating, but not a realistic second Earth or near-term human destination. That's the thesis. 2. How accurate is this? A. Location and basic properties. Pretty solid. Distance, 4.24 light-years away. Correct. Star, Proxima Centauri, a cool red dwarf flare star, about 12% Sun's mass, about 14 to 15% Sun's radius, and 0.0015 Sun's luminosity. Broadly right. Planet, minimum mass around 1.27 Earth masses, orbital period around 11.2 days, orbits in the star's classical habitable zone. Correct. Detection via radio velocity. Correct. Caveat, mass is minimum mass because of the unknown inclination, so the real mass might be higher. B, habitable zone does not equal habitable. Also correct and well explained. HZ just means distance where liquid water could exist given the right atmosphere, not this planet is nice. Venus and Mars are great counterexamples. Both near within the Sun's HC, neither is Earth-like at the surface. The video is right that media simplified in the habitable zone into habitable second Earth, which is not what astronomers meant. C. Tidal locking and the terminator strip. Likely mostly correct, but with some speculative drama added. At an 11-day orbit around a red dwarf, tidal locking is very likely, and that's what most models assume. A tidally locked world does tend to have hot permanent day side, cold permanent night side, a terminator region in between where temps could be moderate. Models show with or no atmosphere, extreme day-night differences, possible atmospheric collapse on the night side. With a thick enough atmosphere and or ocean, you can redistribute heat and the terminator region could be relatively stable, not necessarily a constant supersonic murder hurricane. The script's thin line where one step equals boiling, one step equals instant freezing is an extreme worst-case take. Not impossible, but it's very much on the hell world end of plausible scenarios. Many climate models of tidally locked planets show broader, more moderate twilight zones, if a decent atmosphere exists. So, conceptually right, just dialed up to 11. 4. Proxima's flares and radiation. Core idea is this is really bad news for surface habitability. That's accurate. Proxima Centauri is a hyperactive red dwarf flare star. Observations have seen massive flares, including a 2021 study of a flare that increased UV output by about 14,000 times for a brief time. That's basically the event the video references. Over time, Proxima b probably receives X-ray flux tens to hundreds of times Earth's, extreme UV flux hundreds to thousands of times higher than Earth's average. This is very damaging for atmospheric retention, blowing off the atmosphere and water, surface life, DNA damage, atmospheric chemistry disruption, ozone destruction if present. Where the video simplifies, it more or less assumes no strong magnetic field and no thick atmosphere. Both are unknown. Some research tries atmospheric scenarios with CO2 and N2 atmospheres and finds that if such an atmosphere is present, it might shield surface organisms from the worst UV, at least some of the time. So, radiation blasted, very hostile. Yeah, that's fair. Absolutely surface sterilized hell 100% of the time, no chance? That's a strong claim. A lot of researchers are more cautious and speak in probabilities and parameter ranges. E. Atmosphere and water. Stripped away? The video repeatedly says Proxima b has likely lost most of its atmosphere and water due to intense early flaring, long-term X-ray and UV bombardment, and stellar wind and coronal mass ejections. That's consistent with many recent modeling papers, which do find that close-in rocky worlds around active M-dwarfs are at high risk of severe atmospheric escape. But again, it's modeling plus assumptions. We haven't actually detected Proxima b's atmosphere or lack of one yet. Future big telescopes might finally say something concrete. Subsurface life? The video basically says maybe deep underground on the night side, but probably not because you'd need internal heating and geochemistry, and we don't know if it has that. That's actually a pretty reasonable, we don't know, but don't get your hopes up summary. Subsurface habitability is possible in principle if there's enough internal heating, there's liquid water somewhere, for example, underground ocean, and there are chemical gradients to power metabolism. But we have no direct evidence for any of that on Proxima b yet. So, speculative, but fair that it's a long shot. 3. The distance and interstellar travel part. The numbers are basically right and the spirit is correct. Distance, 4.24 light years, approximately 40 trillion kilometers, correct. Voyager-style speeds, tens of thousands of years to get there, correct. Breakthrough starshot concept, gram-scale cells accelerated by a huge laser array, goal speeds about 0.2 c, travel time about 20 years plus about 4 years for the signal back. Flyby only, no braking. That's all broadly in line with what the Starshot team have discussed. The energy estimates are order of magnitude, the script is intentionally emotive, hundreds of billions of homes, etc. But it's pointing at a real thing. Actual interstellar missions are wildly expensive and technically challenging, especially if you want to bring humans or big payloads. Warp drives, wormholes, correctly categorized as purely speculative and requiring physics, negative energy, exotic matter that we don't know how to realize. Where the video is a bit unfairly absolute, the main scientific tone issues. Proxima b almost certainly cannot support life on its surface. Most researchers would say something like its environment is very challenging for Earth-like surface life and probably strongly disfavors it, not zero chance. There's still parameter space where a thick, well-shielding atmosphere might allow at least microbial surface life, especially in sheltered regions. The Terminator strip as a literal razor-thin line of instant death. Climate models generally show regions of partial habitability, not a knife edge where 10 meters away you die. It is a steep gradient, it's just not necessarily boiling here, instant absolute zero a few steps away, in a realistic atmosphere. Implied certainty about no atmosphere, no water. We haven't observed the atmosphere at all yet. Everything is theoretical. Many papers do indeed lean pessimistic, but they're careful about uncertainties. So, it's not lying, it's just telling the bleak end of the spectrum with maximum rhetorical force. So what should you take away? If I strip out the drama and keep the useful bits, Proxima b is real, close, and roughly Earth mass in its star's habitable zone. Its star is a very active red dwarf that produces huge flares and lots of X-rays and UV. That activity likely makes surface habitability very difficult and may have stripped much or all of any original atmosphere and water. The planet is probably tidally locked, with extreme day-night differences and a complex, possibly violent climate. It is not an Earth 2.0 or a realistic backup planet with current or near-term technology. We still don't know whether it has any atmosphere at all, whether there is water, surface or subsurface, whether any kind of life, especially subsurface, could exist. So the big emotional message is fair. Don't treat Proxima b as our escape hatch. Earth is the only confirmed habitable world we have. Take care of it. If you'd like, I can turn this into a super short summary you can share with friends, or I can zoom in on one aspect, tidal locking, radiation, interstellar travel, and explain that piece more gently or mathematically.
Why scientists think dark matter exists. The transcript walks through the main clues. Galaxy rotation curves. Stars far from the center of galaxies are moving too fast. With only visible matter, those stars should fly off into space. But they stay bound. There must be extra invisible mass holding them in. Galaxy clusters are too heavy. Groups of galaxies move around inside clusters as if the cluster has way more mass than we can see in stars plus gas. Without that extra mass, clusters should fall apart. Gravitational lensing, light bending. Light from background galaxies gets bent as it passes big clusters. The amount of bending shows there's more mass there than the visible stuff can account for. Often, the center of gravity doesn't even line up with where the hot gas is, so something unseen is carrying most of the mass. The cosmic web and structure of the universe. Simulations of the universe only look like our real universe. Filaments, voids, galaxy clusters, etc. if you include a ton of invisible matter. Without it, galaxies don't form fast enough or in the right patterns. Cosmic microwave background, CMB. Tiny temperature ripples in the CMB encode how much matter existed early on. The pattern says there's way more mass than normal atoms can provide. That extra mass has to be non-normal, non-baryonic stuff. Dark matter. What dark matter does, according to the transcript. Think of dark matter like this: a cosmic scaffolding. Ordinary matter, gas, stars, you, your phone, settles into the invisible skeleton made by dark matter. Invisible halos. Every galaxy sits inside a big dark matter halo that extends far beyond where the stars stop, contains most of the galaxy's mass, and keeps stars from flying away and helps spiral arms stay intact. The backbone of the cosmic web. Dark matter clumps and forms dense knots, galaxy clusters, long filaments where galaxies line up like beads, large voids where there's comparatively little matter. Without dark matter, galaxies wouldn't form the way they do. Clusters wouldn't hold together. The giant web structure of the universe wouldn't look like it does. What dark matter is not. The transcript spends a lot of time ruling things out. Not just faint stars, rogue planets, cold gas clouds, black holes everywhere. Those would all interact with light somehow, emit, absorb, scatter, and we just don't see enough of them. Not by itself, neutrinos, too fast, don't clump enough. We just measured wrong. Measurements got better, and the mismatch stayed. Simple, modified gravity, changing the law of gravity instead of adding matter. Some tweaks can explain galaxy rotation curves, but they fail on clusters, lensing, CMB, and merging clusters like the bullet cluster. So dark matter isn't normal matter hiding in the dark, and probably isn't just gravity being weird, at least not in any simple way. What dark matter might be: candidate particles. The video goes through the main suspects. WIMPs, massive, interact via gravity plus weak force, not electromagnetism. Naturally give roughly the right amount of dark matter in early universe calculations. WIMP miracle. Huge underground detectors have tried to catch them. So far, nothing. Axions, tiny, ultralight particles originally proposed to solve a symmetry problem in the strong nuclear force, could act like a field filling space and be dark matter. Might very rarely convert into photons in strong magnetic fields. Experiments are scanning frequencies, like slowly tuning a radio. So far, still looking. Sterile neutrinos. Like neutrinos, but even less interactive. Only feel gravity. Could show up as specific X-ray lines from slow decay. Hints? Maybe. Confirmations? Nope. Yet. Fuzzy or ultralight dark matter? Self-interacting dark matter? Hidden sectors? Supersymmetric particles? Primordial black holes? The video lists a lot of exotic options and shows how many have constraints, some are partially viable, none are definitively confirmed. Bottom line, we have lots of ideas, no smoking gun. Why we're so confident something like dark matter exists. The transcript keeps returning to this core idea. Every time we weigh the universe, using different methods, we get the same answer. Visible matter is not enough. No matter what you do. Galaxy rotation, cluster dynamics, gravitational lensing, cosmic web structure, CMB fluctuations. They all point to the same thing. There is a large amount of mass that doesn't emit or absorb light, doesn't collide or stick to normal matter, does shape gravity everywhere. So even if our interpretation changes, new gravity theory, new particles, hybrid ideas, the gravitational effects themselves are rock solid. Does dark matter really exist then? The end of the transcript is basically a gentle, sleepy philosophy moment. On one hand, dark matter explains an enormous amount of data beautifully. It fits galaxies, clusters, the web, and the early universe all at once. On the other hand, we haven't directly detected a dark matter particle yet. It might be a particle we haven't thought of, several different things, or a sign we need new physics and gravity or the early universe. So the video's emotional conclusion is something like, dark matter is almost certainly something real. But whether it's a new particle, a new law, or a mix of both, we're still in the quiet, patient mystery phase. If you're using this to fall asleep, you can think of dark matter like this as you drift off. The universe is not empty where it looks dark. There's an invisible scaffolding all around, holding galaxies together, guiding where stars form, and shaping the cosmic web. We live in the minority kind of matter. The truly dominant stuff is quiet, patient, and unseen. Our job is not to solve it right now, but to appreciate that.
Deep space exoplanet exploration is the quiet art of finding and understanding planets that orbit faraway stars, and sometimes planets that drift with no star at all. For most of human history, we didn't know if any worlds existed beyond our own solar system. The night sky looked like a scattering of lonely stars, and it was easy to imagine the universe as mostly empty. That changed in the 1990s, when new, ultra-sensitive instruments began to reveal something astonishing. Planets are everywhere. They circle stars of all kinds, orbiting close in or far out. Some move around 2 suns, some around 3. Some are wrapped in oceans hundreds of kilometers deep. Others glow red-hot beneath skies of vaporized rock. Many are too faint to see directly, but we detect them through their effects on starlight. A tiny, regular dimming when a planet passes in front of its star, the transit method. A gentle wobble in the star's motion caused by the gravity of an orbiting planet, the radial velocity method. From these subtle signals, astronomers have gone from 0 known exoplanets to thousands, with billions more likely in our galaxy alone. Deep space is not empty. It is a vast, quiet garden of worlds. How we find invisible worlds. Because planets don't shine with their own light, we study how they change the light of their stars. Transit detection. If a planet crosses in front of its star from our point of view, the star's light dips by a tiny fraction. By watching this dimming repeat over and over, astronomers can tell that a planet is there, how big it is, how much light it blocks, how long it takes to orbit, the time between dips. Stellar wobble, radial velocity. A planet's gravity tugs on its star, causing the star to move in a small orbit. This motion slightly shifts the color of the starlight. Measuring that shift reveals that a planet is there, how massive it is, how close it orbits. These techniques, combined with years of patient observation, have turned tiny fluctuations in brightness and color into maps of distant planetary systems we can't see directly. Reading atmospheres from starlight. Starlight that passes through a planet's atmosphere is changed by the gases it meets. Certain molecules absorb very specific colors of light. When we split the light into a spectrum, a rainbow, those missing colors show up as tiny dark lines, a spectral fingerprint. By studying these fingerprints, astronomers can infer which gases are present: water vapor, methane, carbon dioxide, hydrogen, etc. Whether there are clouds or haze, approximate temperatures, sometimes even hints of storms or climate patterns. This is how we can say, from light alone, that some worlds may have water vapor, thick clouds, or scorching metallic atmospheres. Strange kinds of worlds. The first exoplanets we found were not familiar Earth-like twins, but extreme, exotic worlds. Hot Jupiters. Huge gas giants, similar in mass to Jupiter but orbiting extremely close to their stars. A year can be only a few days. Temperatures high enough to vaporize rock and metals. Supersonic winds and bloated, superheated atmospheres. Their existence forced scientists to rethink how planets form and migrate. Giant planets, it seems, can move inward over time, rearranging entire planetary systems. Super-Earths. Planets bigger than Earth but smaller than Neptune. Very common in the galaxy, yet our solar system has none. Some may be rocky, others may have thick atmospheres or be covered in deep oceans. They come in many forms: lava worlds, thick atmosphere worlds, and potential ocean planets. Their abundance suggests that Earth is not the default rocky planet type. It's just one option among many. Ocean worlds. Planets completely covered in water with no continents at all. Oceans may be shallow or hundreds of kilometers deep. Some may have ice crust with liquid oceans hidden below, warmed by internal heat. These worlds are especially interesting for the search for life, since life on Earth began in the oceans and can thrive even in dark, high-pressure environments. Extreme weather planets. On many exoplanets, weather goes beyond anything we know. Winds faster than the speed of sound, rain made of molten glass, vaporized rock or metal droplets, clouds of silicate dust or iron, giant storms lasting years or centuries. These climates arise naturally from different temperatures, gravities, and chemistries, the same physical laws as on Earth, simply pushed into new regimes. Planets with multiple suns. In binary or triple star systems, some planets orbit just one star, others orbit the whole group. On the surface of such a planet, you might see double sunrises and double sunsets, overlapping shadows, complex seasons shaped by the motion of more than one star. These systems show that planets can form and remain stable even in gravitationally complex environments. Rogue planets. Not all planets have stars. Some drift freely through the galaxy. Most likely formed in planetary systems and later flung out. May still have internal heat and thick atmospheres. Could host subsurface oceans under ice warmed from within. They move through eternal night, lit only by the distant, sharp light of the stars around them. Cold wanderers carrying entire hidden worlds within. Habitability in Earth-like worlds. The habitable zone is the region around a star where temperatures could allow liquid water on a planet's surface. But being in the habitable zone is only a starting point. A planet's true habitability depends on atmosphere thickness and composition, greenhouse gases and cloud cover, rotation, magnetic field, and internal heat, presence of oceans, geology, and long-term climate stability. A planet at the right distance can still be a frozen desert or a runaway greenhouse like Venus. Others, outside of the classical habitable zone, might hide liquid water beneath ice. Atmospheres and signs of life. Atmospheres are key in the search for life. Water vapor hints at clouds or seas. Carbon dioxide tells us about greenhouse warming. Methane can come from geology or biology. Oxygen is especially interesting when found together with gases like methane because they tend to react away unless something keeps replenishing them. Astronomers look for chemical imbalances that are hard to explain without biological processes. Even a subtle, unusual mix of gases could be a clue. Not proof, but a strong reason to look closer. Planetary systems, how they form. Planetary systems begin as vast, cold clouds of gas and dust, nebulae. Under gravity, parts of the cloud collapse and spin into a disk around a newborn star. Inside this disk, dust grains stick together, becoming pebbles, rocks, and finally planetesimals. These grow into planets through countless collisions and mergers. The early system is chaotic. Planets migrate, collide, and eject each other. Over millions of years, the dust clears and the surviving worlds settle into more stable orbits. The tremendous diversity of exoplanet systems we see today reflects these small, initial differences and violent early histories. Alien atmospheres and signs of life. Atmospheres are key in the search for life. Water vapor hints at clouds or seas. Carbon dioxide tells us about greenhouse warming. Methane can come from geology or biology. Oxygen is especially interesting when found together with gases like methane because they tend to react away unless something keeps replenishing them. Astronomers look for chemical imbalances that are hard to explain without biological processes. Even a subtle, unusual mix of gases could be a clue. Not proof, but a strong reason to look closer. How planetary systems form. Planetary systems begin as vast, cold clouds of gas and dust, nebulae. Under gravity, parts of the cloud collapse and spin into a disk around a newborn star. Inside this disk, dust grains stick together, becoming pebbles, rocks, and finally planetesimals. These grow into planets through countless collisions and mergers. The early system is chaotic. Planets migrate, collide, and eject each other. Over millions of years, the dust clears and the surviving worlds settle into more stable orbits. The tremendous diversity of exoplanet systems we see today reflects these small, initial differences and violent early histories. Alien atmosphere.
1. Baby Earth, simple timeline. 1. Solar System soup. Approximately 4.6 billion years ago. Before Earth existed, there was just a swirling cloud of gas and dust around the newborn sun, the solar nebula. Tiny dust grains bumped together to pebbles, to rocks, to planetary seeds, planetesimals. One of those growing seeds would become Proto-Earth. 2. Proto-Earth forms and heats up. Proto-Earth grew by eating other rocks and baby worlds in constant collisions. Each impact equals energy. Earth melts inside, turning into a molten ball. Heavy stuff, iron, nickel, sank to the center, core. Lighter rocks rose to mantle, plus future crust. 3. Magma ocean Earth. The whole surface was basically a planet-sized lava ocean. No land, no oceans, just glowing liquid rock, constantly churning. Thin, temporary crust rafts formed, then melted or broke and sank again. 4. The moon-forming impact, Theia. A Mars-sized world, Theia,
slammed into Earth at an angle. Outer layers of both bodies were vaporized and blasted into space. Debris formed a glowing ring, then gradually clumped into the moon. Thea's core probably merged with Earth's core, changing Earth's interior. The moon started out much closer and has been slowly drifting away since. 5. Heavy bombardment. Asteroid monsoon. Solar system still messy. Big planets, like Jupiter, slung asteroids and comets everywhere. Earth was hammered by countless impacts. Craters formed and then erased by lava. Some impacts created molten rock rain. Comets and rocks delivered new elements and water. Surface stayed hot and unstable, but chemistry was getting richer. 6. First real crust forms. Bombardment slowly eases. Earth cools enough for a thin, fragile crust to form over the molten mantle. It cracks, sinks, reforms constantly, but over time becomes thicker and more stable. Light, silica-rich rocks start forming the first proto-continents. 7. Atmosphere 1.0. Toxic blanket. Volcanoes constantly spew CO2, water vapor, methane, sulfur gases, etc. Result? A thick, hot, poisonous atmosphere. No oxygen, no blue sky. Strong greenhouse effect kept Earth warm even though the young sun was dimmer. Lightning and UV light started driving interesting chemistry in this sky soup. 8. Endless rain and the first oceans. As Earth cools, water vapor in the atmosphere condenses and falls as rain. Not normal rain, millions of years of torrential downpour. Water pools in low areas on the crust and first oceans form. Rain plus rocks equal dissolved minerals, making the oceans chemically rich and salty. 9. Protocontinents and early plate chaos. Lighter crustal material floats higher to embryonic continents rise above the oceans. These protocontinents collide, split, sink, and regrow. Volcanism keeps adding new rock, thickening and stabilizing land over time. The mantle's churning begins to look like early plate tectonics. 10. Interior heat and constant volcanic drama. Earth's inside stays hot because of leftover formation heat, cooling core, radioactive decay of elements like uranium and thorium. This keeps the mantle moving, plates shifting, and volcanoes erupting everywhere. Volcanism controls atmosphere gases, ocean chemistry, how continents grow and move. 11. chemical oceans, the pre-life soup. Early oceans are cloudy, mineral-rich, and weird, not clear blue. Hydrothermal vents on the seafloor pump out hot, chemical-rich fluids. Sunlight, lightning, and heat all provide energy for chemistry. Simple organic molecules start to form, accumulate, and interact in vent systems, shallow pools, tidal zones, mineral surfaces, and clays. Life hasn't started yet, but the ingredients are mixing. 12. Calming down, Earth finds its inside voice. Large impacts become rare. Volcanism continues, but in bursts, not constant rage. Crust thickens and stabilizes. Continents last longer. Oceans develop currents and act like a planetary thermostat. Atmosphere thins and clarifies a bit, still toxic, but more stable. Temperature and chemistry settle into long-lived patterns. Now Earth finally has stable land and ocean basins, a dynamic but not insane atmosphere, long stretches of time without reset button catastrophes, which is exactly what's needed for life to appear next. 2. Bedtime retelling. The night baby Earth was born. You can read this slowly to yourself as a sleep story. Imagine the Earth on the day it was born. Not blue, not calm, not covered in clouds and seas. Instead, picture a world that is glowing. Beneath you, there is no solid ground, only an ocean of molten rock rolling and bubbling like a pot left boiling too long. The whole planet is red and orange, breathing heat into space. If planets could cry, this is what it would look like. A newborn world screaming in lava. Above the glowing surface, the air is almost not air at all. It is steam and rock vapor, thick and dark, shining in metallic colors as the light from below reflects upward. There is no blue sky, no clouds, only a hot, shimmering haze. Far away, the sun is young. Around it, the early solar system is still messy. A swirling crowd of rocks and... Have you ever asked yourself why yesterday is so vivid in your mind, yet tomorrow is completely blank? Or why a broken glass never quietly gathers itself back together? Now picture this. Right now, alongside the reality you're living in, there could be another universe layered over ours, a place where raindrops rise into the sky and where death isn't a full stop, but the beginning of a journey in reverse, all the way back to the womb. My name is Galactic Briefing, and today we're going to explore one of the wildest, most daring ideas in modern physics, a mirror universe that might be sending us subtle signals through the ice of Antarctica. If you enjoy strange cosmic mysteries, weird ideas about time, and crazy-sounding theories that still rest on real science, don't forget to subscribe, hit the notification bell, and travel through the universe with us. Part 1. When the equations don't care about before or after. Take a look at any clock around you.
the ticking second hand, the numbers updating on your phone. We treat time as something obvious and unquestionable, a straight river flowing in only one direction, from past through the present into the future. We're born, we grow up, we get old, we die. No emperor, no genius, no scientist has ever managed to reverse that flow. But here's the strange part. When physicists study the deepest laws of nature, this one-way arrow of time looks out of place. Imagine filming a ball being thrown up into the air, then falling back down. If you play that video in reverse, mathematically, the laws of physics still work perfectly. In Newton's equations of motion, Einstein's theory of relativity, and even quantum mechanics, time can run forward or backward, and the equations remain valid. An electron colliding with another electron, whether you watch it in normal speed or backward, the math has no problem with it. But in everyday life, that's not what we see. A cracked egg never pulls its yolk and shell back together. Cigarette smoke doesn't crawl back into the cigarette. Spilled water doesn't leap back into the glass and stand itself upright. So why do our equations happily allow time to reverse, while reality seems to lock us into one single direction? To answer that, we need to talk about a key concept in cosmology: entropy, a measure of how messy the universe is. Part 2. Entropy, why everything tends to get messier. Think about your bedroom. If you stop cleaning it, dust builds up, clothes pile on the floor, books scatter everywhere. You don't have to do anything for it to become a mess. It happens naturally over time. But to make the room tidy again, you have to spend energy, pick things up, sort them, organize them. That's entropy in action. Entropy is basically a measure of disorder. The second law of thermodynamics tells us, in an isolated system, entropy always increases. An intact glass is a low entropy, ordered state. A shattered glass is a high entropy, disordered state. So the direction of time, the way we feel it, is the direction in which entropy rises. We age because our bodies accumulate damage and mistakes. Cells break down, structures become less perfect. That growing biological mess is also entropy. A breaking egg is the journey from more order to more chaos, and never the reverse. And from this, a giant cosmic paradox appears. If the universe as a whole is getting more and more disordered, then the further back in time we look, the more ordered it must have been. Roll the clock back about 13.8 billion years, all the way to the Big Bang. According to entropy logic, the universe back then must have been extremely well organized, with an incredibly low entropy. But how do we usually picture the Big Bang? A colossal explosion, blistering heat, violent chaos? How could such a violent blast also be the most ordered, most finely tuned moment in cosmic history? The odds that the universe just randomly starts out in this ultra-organized state are unimaginably tiny, so small that it feels almost impossible. Unless our picture of the Big Bang is missing something fundamental. Part 3. What if the Big Bang is a mirror, not a beginning? Some of the leading theoretical physicists have proposed a bold alternative. They suggest the Big Bang was not the single starting point of everything. It's not a solid wall separating nothing from existence. Instead, imagine the Big Bang as a central point, a giant mirror in space-time. At that special point, the entropy of the universe is at its minimum. From this midpoint, disorder begins to spread out in two opposite directions. In one direction, we get our universe, where time flows toward the future as we experience it. In the opposite direction, a mirror universe branches off, where time also flows forward for its inhabitants, but on the time axis, it runs the opposite way compared to us. You can picture it like this. The Big Bang sits at the center of a timeline. Our cosmos expands to the right. The mirror universe expands to the left.
For hypothetical beings living over there, they are born, grow, age, and die. They remember their past and are ignorant of their future, just like us. But if we could somehow step outside and look at both universes at once, we would see them moving in opposite directions in time. Their future lines up with our distant past. Their past sits where we would place the far future. This idea is often called a Janus universe model, named after the Roman god with two faces, looking both forward and backward. In this picture, the Big Bang isn't the beginning of everything, but the symmetry point between two mirror realities. Entropy is lowest there, and then grows in opposite directions along two arrows of time. The beauty of this approach is that it helps resolve the mystery of why the early universe was so strangely orderly, without dragging in divine tuning or bizarrely adjusted constants. It basically says, nature loves balance and symmetry. Where there's positive, there's negative. Where there's positive charge, there's negative charge. So why wouldn't there be a backwards time to complement the forwards one? Observations from the Planck satellite, which measured the faint afterglow of the Big Bang, the cosmic microwave background, show tiny temperature fluctuations that are incredibly small, but extremely uniform across the whole sky. This suggests that the early universe was deeply connected, highly symmetrical, and more orderly than the naive, chaotic explosion picture suggests. Those tiny hot and cold spots are like a fingerprint, hinting at a bigger structure, possibly including the other half of reality that we can't directly see. But if there really is a mirror universe, another question becomes impossible to avoid. What happened to the missing half of matter? Part 4. The greatest disappearance act in the universe, antimatter. When energy turns into particles, our best physical theories say it should create matter and antimatter in equal pairs. But look around. Your home, the air you're breathing, your body, the stars, galaxies, gas clouds. Everything you see is made of matter, not antimatter. So, where did all the antimatter go? Was it destroyed, or is it hiding somewhere we can't reach? To get to the bottom of this, we jump back to the early 20th century. Physicist Paul Dirac wrote down an equation to describe electrons moving near the speed of light. It worked beautifully, but there was something strange about it. The equation had two kinds of solutions, like the equation x squared equals 4, giving x equals plus 2 and x equals minus 2. Mathematically, Dirac's formula predicted a particle with the same mass as the electron, but with positive electric charge instead of negative. At first, people thought he'd made a mistake, but not long after, experiments on cosmic rays found exactly such a particle. It was named the positron, the electron's antiparticle. From there, a deeper realization unfolded. Every proton has an antiproton. Every neutron has an antineutron. Every electron has a positron. Matter and antimatter are like mirror twins, and when a particle meets its antiparticle, they don't merge peacefully. They annihilate each other, turning into pure energy with nearly 100% efficiency, according to E equals mc squared. To get a sense of how powerful that is, nuclear bombs only convert a tiny fraction of mass into energy. If you somehow had 1 gram of matter and 1 gram of antimatter meet, the explosion would rival the bomb dropped on Hiroshima. Now apply this to the early universe. Right after the Big Bang, the universe was incredibly hot and dense. Energy was constantly turning into particles. According to theory, it should have produced equal amounts of matter and antimatter. If that were true, then as the cosmos cooled, matter and antimatter should have met and annihilated each other completely, leaving behind nothing but radiation, no stars, no planets, no life. But clearly that didn't happen. We're here, in a universe overwhelmingly made of matter. Antimatter is rare, found in a few cosmic rays or created briefly in particle accelerators. Physicists call this issue the baryon asymmetry. Have you ever asked yourself a simple but unsettling question? Where is everything in the universe actually going? Not just the Earth, not just the Sun, but everything. Our galaxy, nearby galaxies, entire clusters and superclusters of galaxies, all drifting through space along paths we are only just beginning to understand. Back in the 1970s, astronomers noticed something strange. They realized the Milky Way isn't just quietly orbiting along, minding its own business. It's racing through space at an enormous speed, and not randomly, but seemingly pulled toward a particular region of the sky, a place hidden behind the dust of our own galaxy, where ordinary telescopes see almost nothing. That invisible destination was eventually given a dramatic name, the Great Attractor, a mysterious region whose gravity seems to tug on thousands of galaxies at once. But that's only the beginning of the story. 1. The universe is moving. A lot. I'm Your Name or Channel Name, and you're watching Channel Name. Today, we're going to follow the cosmic currents, from the motion of Earth beneath your feet to the dance between the Milky Way and Andromeda, to vast structures like Laniakea and Shapley, all the way out to the ultimate fate of our universe under the rule of dark energy. If you enjoy deep dives into space, time, and the big questions of existence, don't forget to subscribe and hit the notification bell so you don't miss future journeys. All right, let's orient ourselves. We often live as if we're standing still, as if the ground beneath us is fixed and the sky turns around us. For thousands of years, people believed exactly that. Earth at the center, sun, moon, planets, and stars orbiting around us. To match the strange loops and zigzags of the planets across the night sky, astronomers of the past invented constructions full of circles upon circles, epicycles, a complicated, fragile model trying to preserve the idea that Earth is still. Then, in the 1500s, Copernicus proposed something radical. The sun, not the Earth, is at the center of the planetary system. Suddenly, things became much simpler. But new problems appeared. If Earth is moving, why don't we feel it? Why aren't we blasted by some cosmic wind? Why don't we get flung off into space? It took centuries, and eventually Newton's laws, to frame the answer. We don't notice Earth's motion because everything around us is moving along with it. There's no air resistance in space like there is on Earth when you run. In the vacuum between planets, there's nothing to push against, so motion feels like nothing at all. But that raises a deeper question. How do you even know whether you're moving in the first place? Is there a cosmic zero point of absolute rest? 2. From Newton's fixed background to Einstein's relativity. Newton imagined that, yes, there is a kind of invisible absolute coordinate system, a cosmic grid against which all motion could be measured. Then along came Einstein, and he broke that idea. According to relativity, there is no universal at-rest frame. Motion is always relative to something else. If you're floating in a spaceship with no windows, drifting in deep space with no engines on, and another ship passes you, you can say, they are moving, I'm stationary. Or they can say, we're stationary, you're moving. Both statements are equally valid. Physics doesn't privilege either point of view. We can still detect rotations and accelerations. For example, Earth's spin shows up in the Coriolis effect, which influences winds, storms, and ocean currents. But when it comes to large-scale straight-line motion, there's no obvious reference point. Unless we use the universe itself. 3. The universe as a cosmic reference frame. We live in a universe that is expanding. On the largest scales, galaxies are being carried away from each other by the stretching of space. This expansion gives us a natural cosmic rest frame, the frame in which the average distribution of galaxies and the cosmic microwave background look as uniform as possible. Any object that has extra motion on top of that expansion has what astronomers call a peculiar velocity, its own additional drift of a few hundred or even a few thousand kilometers per second. To understand where we're going, we need to know how Earth spins, how Earth orbits the Sun, how the Sun orbits the Milky Way, how the Milky Way travels among other galaxies, and how all of that compares to the smooth expansion of our universe. Let's break that down. 4. How fast are you moving right now? Even standing still in your room, you're in constant motion. Earth's spin. At the equator, the surface of Earth rotates at about 1,600 kilometers per hour. At mid-latitudes, the speed is lower, but still close to 1,000 kilometers per hour. Near the poles, it approaches zero. Over an average lifetime, you'll travel about 1 billion kilometers just from Earth's daily rotation. Earth's orbit around the Sun. Earth orbits the Sun at about 30 kilometers per second, over 100,000 kilometers per hour. Over 80 years, that adds up to roughly 80 billion kilometers traced out along our planetary path. The Sun's path through the Milky Way. Our star isn't sitting at the center of the galaxy. It orbits the Milky Way's core roughly once every 230 million years at a speed of about 220 to 230 kilometers per second. That orbital speed is actually one of the crucial clues that revealed the existence of dark matter. If we count up all the visible stars, gas, and dust, there isn't enough mass to hold the Milky Way together at those high speeds. Without extra invisible mass, the galaxy would slowly fly apart. So the Sun is orbiting, bobbing up and down through the galactic disk, and weaving through regions of gas and dust. Right now, our solar system is passing through an unusually low-density region called the local bubble, a cavity in the interstellar medium likely carved out by supernova explosions millions of years ago. And beyond all that, the Milky Way itself is on the move. 5. A date with Andromeda. Our nearest large galaxy neighbor, the Andromeda Galaxy, is not calmly floating away from us with the overall expansion of the universe. It's actually coming toward us. By carefully measuring the galaxy's light, especially the radio emission from hydrogen, astronomers have determined that Andromeda is approaching the Milky Way at a speed of roughly 100 kilometers per second once we correct for our own motion around the galaxy. For a long time, we only knew its motion along our line of sight, whether it was coming closer or moving away. We didn't know how much it was moving sideways across the sky. That changed when the Hubble Space Telescope was used to track the tiny shifts in the positions of Andromeda stars over many years. Combining all that data, astronomers concluded a collision between the Milky Way and Andromeda is not just possible, it's inevitable. In roughly 4 to 5 billion years, the two galaxies will begin a long, complex interaction. Their shapes will be distorted. Long tidal tails of stars will be pulled outward. Gas clouds will crash together, triggering bursts of star formation far more intense than what we see today. The sky from any surviving planet would be spectacular, Andromeda stretching across much of the sky, warped and twisted, new bright massive stars igniting like cosmic fireworks. After a series of passes and interactions over hundreds of millions of years, the two spirals will eventually settle into a new form, likely a giant elliptical galaxy. Astronomers sometimes jokingly call this future merged galaxy Milkometa. But this grand merger is just a local episode in a much bigger cosmic story. 6. From local group to superclusters. Our Milky Way and Andromeda are part of a small galactic family called the Local Group, which also includes the Triangulum Galaxy and dozens of smaller dwarf galaxies. The Local Group itself is not isolated. It's being drawn toward the nearby Virgo cluster, a massive cluster containing thousands of galaxies. But even Virgo is part of something larger. For decades, astronomers noticed that large numbers of galaxies seem to be flowing in a particular direction in space, toward a blurry region hidden behind the Milky Way's dust. This region was nicknamed the Great Attractor. Using improved galaxy surveys and clever mathematical techniques, originally developed for optimizing transport and logistics, astronomers like Brent Tully and collaborators have reconstructed the large-scale motions of tens of thousands of galaxies.
From this, they identified the supercluster of structures we belong to and gave it a name, Laniakea, Hawaiian for immense heaven. Laniakea isn't defined just by where galaxies are, but how they move. The local group is bound to the Virgo cluster. Virgo and other clusters are all flowing toward a common gravitational basin. Altogether, about 100,000 galaxies extending over some 500 million light-years form this giant supercluster-scale region. At the center of this flow appears to be a massive cluster called Norma and nearby related structures. This central region is closely associated with the Great Attractor, yet even that might not be the final story. There's an even larger concentration of mass further away, the Shapley supercluster, one of the most massive structures known in our cosmic neighborhood. Its gravity also tugs on us, possibly shaping our motion along with Laniakea.